Hey everyone, Geek37 back with another video. Now, what I'm going to do today is I'm going to take three identities that I derived earlier in the series, and I'm going to do an extension from variables into trig ratios. So here's what I'm talking about. This interesting looking identity, c squared minus 2a squared equals the square root of 7ar, is in its variable form. Now here's how we will turn it into its trig ratio form. What I'm going to do is I'm going to divide everything by AR. Now, before we go any further, let's establish the fact that A is the length of the short side of the heptagonal triangle, C is the length of the longest side of the heptagonal triangle, and R, while not shown in the picture, is the circumradius of the heptagonal triangle, which is outside of the triangle because the triangle is obtuse. So coming back to this, we have c squared over AR minus 2a over r equals the square root of 7. Now, if you remember from the last video I did, that c squared over ar should actually look familiar. C squared over ar is equal to the tangent of 3 pi over 7, and because of the way the sign ratios work, it is also equal to the tangent of 4 pi over 7. So what I'm going to do is I'm going to replace the c squared over ar with the tangent of 4 pi over 7. Now take a look at this 2a over r. You have, we don't really have anything to associate with that, but here's what I'm going to show you. Going off to the side here, we have 2a over r. What happens is if you take a 4 out from that, what happens is you'll get a over 2r on the bottom. So if you factor out the 4 from the fraction, the 2 on the top goes to the bottom because 4 divided by 2 is 2, and that original 2 is in the numerator. But as you notice, a over 2r is equivalent to the sine of pi over 7. So the tangent of 4 pi over 7 minus 4 times the sine of pi over 7 equals the square root of 7. And because of the way tangent is, you can also rewrite it with 3 pi over 7 as well. Now, when I first saw this equation a number of years ago, I had no idea how it was derived. It is one of the most fascinating and strange-looking trigonometric equations I had ever seen. And what happened is when I first encountered it, I used the law of cosines and a whole bunch of stuff that I've derived from the heptagonal triangle earlier in the series to come up with that. But recently, by just looking at the AR part on the back, I was able to do the division and make it that simple to come up with those two equations. Now, we're going to derive two more identities that are associated with the triangle with that square root of 7 form. Give me a second here. So now I'm going to do the second equation, 2b squared minus a squared equals the square root of 7 times br, and of course b is the length of the medium side of the heptagonal triangle. So what we'll do is we'll do the same thing like I did on the last part of the video. We'll divide by br. We want to get that square root of 7 by itself. So here's what happens. The BRs will cancel. 1b will cancel out here. So here's what we have. We have 2b over r minus a squared over br equals root 7. Now, of course, we know that a squared over br from the last video was equivalent to the tangent of pi over 7. And if you look at 2b over r, it has a similar form of 2a over r. So what I'm going to do is I'm going to factor out the 4, and then I'll get b over 2r. And of course, if you remember, b over 2r is equivalent to sine of 2 pi over 7. So it'll be 4 times sine of 2 pi over 7. So what happens is, let me actually just draw it up here so we have the space for it. We will get 4 sine 2 pi over 7 minus tangent of pi over 7 equals the square root of 7. So this is the second equation. And this might have actually been the first equation that I saw of this type years ago. And again, a very simple derivation. And of course, when I first encountered it, I went through this long entire derivation to get that answer. But again, quite a fascinating equation that people don't really see all that often. And I'm wanting to show you all this stuff today. Okay, so let's get the next one done, and that'll conclude the video. Okay, and we will do the last one here. We have 2c squared minus b squared equals 7, square root of 7 times CR. Oops. Sorry. So we got 2c squared minus b squared equals the square root of 7 times c times r. So what we're going to do is we're going to divide everything by CR here. The CRs will cancel on the right side, and the C will cancel on the first part of the equation. So we get 2CR minus B squared over CR equals the square root of 7. Well, if you remember from the last video, we know that B squared over CR equals the tangent of 2 pi over 7. And of course, like the last two examples, we can factor out a 4. So 2c over r becomes 4 times the quantity c over 2r. So that makes that 4 times the sine of 3 pi over 7. But of course, again, 3 pi over 7 is also equivalent. The sine of 3 pi over 7 is equivalent to the sine of 4 pi over 7. So that'll also give us two versions of this equation. So we can rewrite it as, first off, 4 sine 4 pi over 7. I'm going to do that first because of this series is about the heptagonal triangle, minus tangent of 2 pi over 7. And the next one is 4 sine 3 pi over 7 minus tangent of 2 pi over 7 will equal the square root of 7. And of course, I forgot the square root of 7 here. So that is basically 5 equations, but really there's 3 equations here that all have the square root of 7 and different versions of the angles with sine and tangent to create that. And again, I still find all of these equations fascinating because I didn't realize you could take two separate trig ratios like this, subtract them, and get a simple square root. You do have to multiply the sine part by 4 to eventually get to that square root, but it's something I never would have expected in all of my years of doing math. And even though I've known about these for about half a decade or more, it still blows my mind. And I just wanted to show that to you today. All right, I hope you enjoyed this video. I enjoyed making it. This is Geek37 signing off.